All right. In this video, we're going to talk about the OSEMN pipeline. Um, we're going to talk about several frameworks in this class as far as the way people approach the analytics life cycle or the analytics project. And this is one of the more popular, or at least one of the more visible frameworks that is out there right now. Now, the OSEMN pipeline is not especially different than other data science life cycle kinds of models, right? And basically, the OSEMN is obtain, scrub, explore, model, and interpret. Now, I'm going to tell you right now, you're going to spend the huge majority of your time on most data science projects on the obtaining and scrubbing component of this. At least for now, in this 2020, as when I'm recording this, up to 80% of your data that you're going to be needing for your projects is, up to 80% of your project timeline is going to be spent on obtaining and scrubbing your data. Now that seems to be annoying because obtaining and scrubbing the data provides no value to your customer, right? Whether it's a business client or it's it's some sort of a science organization, whatever it is, obtaining and scrubbing the data provides no value. And so spending 80% of your time on that is probably the biggest problem in analytics right now. If analytics, my daughter is a data scientist for the government, and she says, well, if analytics is Superman, the obtaining and scrubbing of data is kryptonite, right? So anyway, this is a typical problem, all right? Now, we're not going to spend a ton of time on each of these steps because they're kind of self-explanatory. We have to, for every analysis, obtain data. Now, that data might be data you already have internally. It's most likely going to include more than one data source, and getting those multiple data sources, even if they're clean and they're internal, getting them into one place for you to work on, getting them linked together and joined and ready to go is going to take time. You're probably going to have to generate additional fields, dummies, one hot encoding, different kinds of metrics, of text kind of things. And of course, you're going to have to identify gaps and go get more data. All right. Why would you do this per analysis rather than all at once? Well, one of the reasons is that requirements change so fast, and business questions or business priorities or analyses, the priority of those things change so fast that spending months and months gathering all the data you think you might need for a project is probably the wrong way to go. What you probably want to do is approach the analysis question by question and allow the users to reprioritize each time that you finish a question, because the likelihood is that your completion of question 1 is going to lead to maybe different questions for question 2 and question 3. And so if you spend too much time up front on getting the data for 11 or 12 or 15 different research questions, a lot of that might end up being just wasted effort. You might never need some of that data, all right? It happens very often that, okay, we want this project to handle these 14 research questions, but once we answer about 7 or 8, we go, we know enough now. We don't need to do the other research questions that we'd originally planned. So you usually want to approach these things one question at a time, because then you start delivering value faster, all right? So the kind of technical skills that you're going to have to deal with in the obtain is, how do you access SQL databases? How do you use Python to scrape some data? We'll do both of those things, at least introductory examples of those things in this course. Hadoop, if working with big data, which we'll cover in the data management program, etc., and the data management class, right? Now, the best practice is to fully document the source of every field in your data, okay? Now, it could just be in commented code, but in reality, there's going to be different requirements depending upon the organization you're in or the client that you're working with. And you will want to make sure that you can hand off a project at any time and be able to allow the next person working on the project to know where the data came from. All right? Now, again, between obtaining and scrubbing, up to 80% of project time is spent here. Now, the most important technical component of this pipeline is scrubbing, because good data is more important than any method you might use. Because the worst possible thing we could do is come up with some really cool models and some really cool analyses that tell us how to do the wrong thing faster, right? So we must scrub the data, and we must realize that this is something you've heard 1,000 times: garbage in, garbage out to that database. Now, what are some of the real basics that you do? Trim extra spaces, how do you deal with blanks, right? How do you deal with missing data? Do you just impute? Do you add the mean value? Do you leave it blank and use an analysis technique that allows you to leave it blank? Convert numbers stored as text into actual number values, etc. You can see all these different things: making text consistent, getting rid of formatting, and all of these things are things that you can do in Python or R, right? Or in many other ways in SQL, different things, right? So you're going to be spending a significant amount of time in this scrub area. Now, it's very important to have high quality information. And there's typically considered 5 characteristics of high quality information. The first is that it's complete. Now, data completeness simply refers to whether there are gaps in the data from what was expected to be collected, or what you expected to get when you obtained data, and what you actually got. So here's an example. An inspection is done on a vehicle, and the inspector accidentally does not indicate the hour meter reading on the vehicle, which is a required field for that inspection. Now, this inspection is incomplete, and that information is not there, and so that record can probably not be used in analyses that have to do with when do parts have to be replaced, how long is too long to wait for a different kind of maintenance on these vehicles, etc. And again, even worse than not obtaining the data is spending the money and time to obtain data and not getting the data you need. Now, accurate data has to deal with whether or not it's correct and represents what it should. So you collected it, is it now accurate, right? So looking again with that vehicle inspections theme, if we create that inspection and put a value in for every field, but you don't spell things right, or you use different, so this is a very common thing when databases don't enforce rules of accuracy. It's a very common thing for people to put phone numbers in different formats, and of course one person generally is mostly consistent, but when you have 8, 9, 10, or 100 people entering data, that consistency becomes a problem and that accuracy becomes a problem, right? So it's fine if your database is enforcing things, but one of the things the database could never enforce is whether the person puts the right numbers in. A database is going to enforce, is this a number? Is this a number in a reasonable range? So, for instance, you might say, well, none of these vehicles have 1 million miles on them, so you wouldn't allow somebody to type in 1 million miles. But how are you going to keep somebody from typing in 40,000 when it should be 60,000? It's very difficult unless you're using technology to monitor these things, which many people do now. Now, consistency. Now, consistency is important in a variety of ways, right? So, thinking about completeness, it's a little different, right, than completeness. Consistency has to do with the idea that um, if you're looking at data one way, like by state, and then you're looking at the same data by city, the data should be consistent. So if you look at all the cities in South Carolina and you add up some sort of a metric for those, when you add it up for South Carolina, it should match the sum of the ones that are in the cities, for example, right? And again, consistency is, again, like we talked about in the previous one, it could just be from the way people put in the data, etc. Right? Now you're going to learn all kinds of ways to enforce these 5 rules of the characteristics of high quality information, but nothing is going to keep. You can enforce those things 1,000 different ways, but there's no way you're going to know. Consistency is one you can definitely enforce, but you're not going to know what humans might do to get around your different restrictions, right? Now, the last thing is timeliness. Sorry, not the last thing, but the next thing is timeliness. And we often think about getting data we should do that as fast as possible. We should always have data updated every day or every week. And that's true in some ideas, in some questions about whether you need things as far as like daily sales predictions and things like that. Well, maybe you do need yesterday's data. But on many analyses, no one's going to be looking at those more than once a month, once a quarter, not frequently. And so you just need to make sure that if a question needs to be answered every week, that you have data every week. And honestly, you should be as slow with your data as possible, because the faster that you need to collect data, the more real time your data needs to be, the more expensive that's going to be, and the more administrative overhead you're going to have. Now, the last one is data validity. And data validity is trickier because sometimes we can't measure what we need to measure. Maybe some things are impossible to measure directly. So this is definitely, so that the typical example is, how do you measure intelligence? You can't just measure intelligence directly. So there's several different factors that we've made the assumption, or at least we've kind of made the theory that, well, if you measure this and you measure this and you measure this, that's a good proxy for intelligence. Now, most of the things that we're going to be looking at, hopefully, are dealing with things that are measurable, right? But the example here on the screen is a very typical one, where we used to collect 7 fields about this thing, 7 fields of data, but now there's a new government regulation that requires us to collect an extra 10 fields. Now, starting from now, we can collect those 17 fields, but the data before then is likely not going to be able to be included in some analyses that are required. And you may have to be able to go back and fill that information in if there's a way to do that, or you're simply not going to be able to include that data in your analyses. Now, as I mentioned, databases contain rules that help us to enforce the characteristics of high quality information, but, and we'll talk more about relational databases in a little while, in a few weeks, or sorry, not a few weeks, in a few modules. And from that point, we'll talk about this a little bit more. Now, one of the problems that we're going to deal with in analytics these days is that we're getting more and more and more data, either millions of records or millions or thousands of columns of information, and that data sometimes becomes unmanageable for things like scrubbing, right? And so let's say you have millions and millions of records, and you can't figure out all the problems that might, or you can't search through all the data to understand all the problems. So do you have to examine every row? Probably not. A best practice is that you can randomly sample 1 to 2% of your data, and that 90% of your data issues are going to be present in this sample. Because data issues are typically systemic. They're not random. They're typically, we always mess up this kind of data. Or this data from this factory is always got a data problem, or is where our data problems are most common. And so what you can do is you can take 1 to 2%, you can sort out what you have to do there, and then you can manage by exception as you're running bigger and bigger sets of your data. Now, as far as scrubbing, your technical skills that you're going to apply are things like Python, R, etc. And you're going to deal with pandas, Alteryx, which is a workflow, a data management workflow application, Tableau Prep, which is the same kind of thing. And there's tons of ways you can scrub your data. Don't use Excel, even though you can, unless you're dealing with a very, very small set of data. I would argue that you should always do this in code that you can review, and that you should always include assumptions and why you're doing particular steps in your code based around your understanding of the requirements of the project. That way, honestly, in 2 or 3 weeks, when somebody asks a question and you can't remember how you got a particular number, which is very common if you're dealing with many fields, it's like, what did I do with that? Go back to your code and look at your comments and understand exactly what you're doing. That's the main reason I say don't use Excel, because you'll never perfectly document all of the different formulas that you're going to use in Excel to clean things up. All right. So again, write that code in a way that you can audit it and re-execute it against the source data. When I do analyses, I never touch the source data. I never modify it. I put the source data in kind of a lockbox, and then I write code that scrubs it, and every single time I run the analysis, I run the scrub. So I'm never changing that data. I only ever have one set of data, and I re-execute that scrub every single time. Now, I'm only dealing with thousands of records. You might not be able to do that with millions and tens of millions of records, but in general, that's what I try to do. And again, the biggest possible thing, if you learn nothing else from this lecture, is to be paranoid. Double check, triple check, quadruple check that your scrub is doing what you think it's supposed to do. This is the thing I learned that was most important when I was in industry and I was working on this, was to increase my level of paranoia every day. Because if you're paranoid, you catch the problems that people who think they know exactly what they're doing all the time and know everything don't catch. All right? So take the time to do the scrub right. Comment what you're doing so that you can audit it. And we will be doing some data scrubbing in this course, and I want to see comments about what you're doing where. All right? That'll be part of the assignment. All right. Now, after you scrub, you get to finally explore. Now, you're going to spend tons of time in your statistics and your machine learning classes on making sure that you can explore your data and understand what your fields or your features consist of, right? There's lots of assumptions that you have to meet in order to do different kinds of analyses. Some require normal distributions of variables. Some aren't appropriate for continuous dependent variables versus categorical dependent variables. Some need to deal with outliers differently, or you might need to remove them. And maybe you're going to see a pattern or a trend that you don't expect in the data that kind of illustrates that there might be another mechanism in play in the generation of data, and it might violate certain assumptions of independence, of error terms, and other things, right? Next thing you'll want to do, and again, you'll do this in your statistics class, is use Tableau or other tools to visualize what you find. You will visualize things over and over and over again in this exploratory phase. Now, to do the exploration, again, the reason we're teaching you Python and R is because you can pretty much do everything a data scientist needs to do in those tools, all right? look for spurious patterns, use data visualization, because honestly, the only way that you will be able to make sense of series of data instead of individual values is through visualization. Finally, we get to the fun part, the modeling. And there's really only two kinds of analyses that you're going to do. You're going to do classification problems, and you're going to do quantitative prediction problems, regression kinds of problems. Now, the difference is that between those is that a classification problem focuses on taking a particular record, maybe a particular customer record, a particular reading of an experiment kind of record, and you'll want to put it into one of a set of groups. Now, that could be like, is this application going to end up with a good loan or a bad loan? And for that, you're probably going to use some flavor of logistic regression. Customer similarity. So you've got some predefined groups. I've got my good customers. I got my bad customers. I've got my medium customers. And when I get a new customer in, which group is that customer probably going to fit into? And so in that case, you have kind of these predefined groups. A very similar kind of analysis is cluster analysis, where you're kind of exploring your customers and you're saying, what groups do these fall into? We don't really know what groups our customers fall into. And so that kind of analysis, again, is exploratory, and you use a cluster analysis for it. Now, in all those cases, you're putting a particular record into one of a set of groups. Now, the other kind of problem that we're going to be working with are quantitative prediction problems, where we're looking for some value. Instead of saying, does this record belong in a 1 or a 0 or different kinds of groups, it's, hey, based upon these characteristics, maybe person's credit score, how much of a loan should I provide that person? So we're dealing with a kind of a continuous variable that's going to actually be a number, a predicted number at the end. So how much will a customer use a service? What's the predicted annual sales for a client with these characteristics? And those are the two kinds. It's classification problems and prediction problems. And fundamentally, that's it. There's a lot of flavors to those, but fundamentally, those are the kinds of problems you're going to be working with. And then finally, interpretation. You're going to do all kinds of models. You're going to need to use interpretation, and you're only going to be able to interpret things if you have proper knowledge of the context that you're working in. And we'll talk about, how do you get experience and expertise in the context a little bit later. All right. Now, interpretation is the main thing that we're getting to, right? We model not for the sake of modeling. We model to get to an answer or to a number or a pattern that we're going to either confirm or disconfirm our hypothesis or the conventional wisdom. We think the world works this way. It doesn't work this way. We think the world works this way. It does work this way. And the most important thing that interpretation is going to do is it's going to lead you to what the next question is. And because it is kind of a sequential thing where one question leads to another, that takes me back to the obtaining and to all of these pieces of the pipeline. You want to work as much as you can, one question at a time. All right. So the OSEMN pipeline is one of a number of models that's used to describe the analytics lifecycle. And again, you're going to come back to this numerous times throughout the program. All right. And that's it.